I'll hand it off to our first session chair, Larry Smith, who will chair this morning's session. Thank you very much, Larry.
Good morning, everybody. Our first speaker is Dr. Debendra Das Sharma. Debendra is an Intel Fellow in the Data Platforms Group and Director of the I/O Technology and Standards Group at Intel Corporation. He drives PCI Express, Compute Express Link, CXL, Intel's Coherency Interconnect, and Multi-Chip Package Interconnect. He's a member of the Board of Directors of PCI SIG and a lead contributor to PCIe specifications since its inception. He's a co-inventor and founding member of the CXL Consortium and co-leads the CXL Technical Task Force. Dr. Das Sharma holds 148 US patents and is a frequent keynote speaker, distinguished lecturer, invited speaker, and panelist at the IEEE Hot Interconnects, SNIA STC, PCI SIG Developers Conference, CXL Consortium events, Open Server Summit, Open Fabrics Alliance, Flash Memory Summit, SNIA STC, and Intel Developer Forum. He has a Bachelor of Technology in Computer Science and Engineering from the Indian Institute of Technology in Kharagpur, and a PhD in Computer Engineering from the University of Massachusetts in Amherst. He has been awarded the Distinguished Alumnus Award from the Indian Institute of Technology in Kharagpur. Debendra, take it away.
Thank you. Larry, can you guys hear me? If you can just give me the privilege to share my screen.
You should be able to share your screen now.
Yes. Looks like something happened. So I'm assuming you guys can see my screen. Okay. No. All right. So let's get started. Hey, greetings. My name is Debendra Das Sharma, and I'm excited to participate in IEEE 3DIC conference. I wish I was there in person. I had some personal conflicts, maybe next year. I hope everyone is staying safe and healthy. I'll talk about the future challenges for on-package interconnects. In my mind, there are tremendous opportunities that we have in front of us with on-package interconnects. I'll draw on my experience of more than 2 decades of driving successful multi-generational industry interconnect standards like PCI Express and recently Compute Express Link in terms of what we can do to drive a thriving chiplet ecosystem going forward. Here is the agenda for today. We will take a look at the compute landscape and where does the broad class of interconnects fit in that landscape. Next, we will delve into on-package interconnects, the opportunities and challenges, the opportunities it presents, and the challenges that we need to overcome in order to drive such a thriving interconnect, thriving chiplet ecosystem. Then I'll get into what an essential ingredient, which is how do you standardize for a chiplet ecosystem. I'll also go out on a limb and talk about some future directions and then conclude. When we look at the industry landscape today, we see some mega trends that are clearly emerging. Cloud computing has become ubiquitous. Networking and edge computing are exploding, and they're increasingly using the cloud infrastructure. AI and analytics to process that data is driving a lot of innovations across the board. All of these are demanding faster data processing entities, which are resulting in the deployment of custom heterogeneous computing solutions in addition to the traditional CPUs, things like GPGPUs, ASICs, FPGAs, all of those. Now, in addition for the heterogeneous computing demand, we are also seeing the demand for increased memory capacity and increased memory bandwidth in our platforms. There are significant technical innovations in the area of storage class memories that have resulted in those memories approaching DRAM-like latency and bandwidth with non-volatile characteristics. That's essentially creating a separate memory tier. And the confluence of these things are helping us solve a wide range of problems effectively to address the fact that data is exploding, whether it is cloud, whether it is 5G, whether it is data from sensors, whether it is automotive, whether it is IoT. All of these applications are demanding very aggressive time to gain insights in real time in these large data sets. So we are left with having to solve these scaling challenges, whether it is latency, whether it is bandwidth, whether it is capacity, in order to meet the customer demands with rapid innovation. So as a result, we have to move the data faster. We have to store more data. We have to process all this data quickly, seamlessly, efficiently, and securely. And we also have to determine where in the storage hierarchy we need to store this data. Now, in each of these aspects, interconnects play a very important role in the compute continuum. Now, I was mentioning Compute Express Link, and we have seen basically Compute Express Link emerge in this context to address the challenges in this evolving landscape. It makes two things happen. It makes the heterogeneous computing a part of the coherency domain, we'll see that. And also it makes all different types of memory efficient and sustain the needs for many years to come. So the question here in front of us is, do we need to do something similar, ground up, to address these challenges on package? Some of them are fairly obvious. For example, we need more memory bandwidth. As a result, we have things like HBM. But can we do something concerted for things like processing, for memory, for connectivity on the package, similar to what we have done on at the node level or at the board level? The picture here shows the interconnects at different levels of the data center, looking from outside in. So this is the left picture here. Not sure whether my cursor is moving or not. But so a data center consists of pods, and each pod consists of racks of servers here. They're all connected through networking fabrics where we use optical connections for longer distances and copper for short distance. Now, each rack consists of multiple chassis, and each chassis is like a node. And a NIC, typically a network interface card, it connects to that particular drawer or that chassis into the networking infrastructure of that data center. Now, the compute drawer the drawer can be a compute drawer, it can be a memory drawer, but all of them basically have computing element, memory element, and storage element. It is just that, what purpose are they used for? Now, even though this is a data-centric picture, other things like edge and on-premise computing, they're also using similar infrastructure. Maybe the scale is just different. Now, each server in this rack that is there in a particular node, or we call it a node or a chassis or a drawer, these terms get used interchangeably. Each of them consists of one or more CPUs. So this is another cartoon picture on the bottom right here. One or more CPUs. It has got its own attached memory devices. If you got more than one CPUs, you connect them through a CPU to CPU cache coherent link, like our ultrapath interconnect or UPI. There are multiple cards. They can be PCI Express cards. So these are like your GPGPUs, NIC devices, storage, all of those, right? So those are devices, whether it is Compute Express Link or PCIe. So all of these are what I call as the load store interconnect, in the sense that they carry direct memory access semantics in some flavor. Today, and by the way, all of them have converged on a PCIe PHY, as you can see here. It's the same PHY, just different protocols running on top of it. So today, none of these memory resources or none of these IO resources, they can be shared between nodes. They're all captive to that particular node. So for example, if I have got 100, or let's say, in a typical rack, you're going to have 16 or so nodes. None of them can share the other person's memory if they have a need for a larger memory footprint, for example. So these are all captive resources. So as a result, what we have is stranded or overtaxed resources in the rack or in the data center. And this is resulting in inefficient use of the compute capability, compute storage and memory capability that exists in that data center or in that edge or whatever exists. So the goal is to get better efficiency, and that's where CXL come into picture here. And you can see that that's basically extending that load store semantics from that node level or from the level of the chassis into the rack and potentially into the pod level. And it is basically what it does is it enables multiple independent hosts, as shown on the picture on the top right here, to effectively give the load store semantics. And with the development of a switch, you can now basically have the resources that are on the bottom side of it be dynamically. You can move them between these different hosts. So for example, in this picture, D1 is assigned to H2. And this can be a GPU. And over time, when H2 does not have as much of a compute need, you can release D1 into the pool, and maybe D1 gets assigned to H4, in which case it will be colored the orange color. So bottom line is, with CXL, we are moving load store IO from each and every one of the chassis level into the rack level and potentially beyond. So then the question is, what happens at the processor or at the package level, at the SoC level or at the package level? Now, there also we see today, the reality is that there is deployment, widespread deployment, in fact, of on-package interconnect, as you can see over here, right? So we do deploy on-package interconnect, and these are today done to stitch homogeneous as well as heterogeneous dies. Dies that do logic, separate dies that do potentially memory, separate dies that do connectivity. So we do stitch them together. And the question is, do we do that in a concerted way where they all interoperate with each other, or do they just do their own proprietary interconnect? And it's a use once kind of a mechanism that we have. By properly doing this, it will basically enable us to build scalable system. And my vision is that the load store IO basically, just like it went from the node level all the way to the rack and beyond, we need to think about plug and play dies that can talk to each other at the package level. And that's basically what I will delve into in this particular talk. Now, let me switch my gears a little bit and talk about the taxonomy of the different types of interconnect and identify some of their key characteristics and differences. I would categorize the broad wired interconnect world, and this is at the board level, into board or beyond level, into two categories. One of them is the latency tolerant, which I'm calling the networking, and the other one is latency sensitive, which I'm calling the load store IO. And the fundamental reason stems from the scale in which they're deployed. This is resulting in some of the key differences and characteristics. So whether networking interconnect, whether it be in one of the flavors of Ethernet, InfiniBand, OmniPath, it needs to scale in its connectivity to hundreds of thousands of nodes at the data center level. Hence, what happens is they're narrow. They tend to lead the speed transitions, often at the expense of latency and cost. Now, in contrast, if you look into the broad class of load store IO, these are latency and cost sensitive, things like PCI Express, CXL, CPU to CPU symmetric multiprocessing link like UPI, or any other memory interconnect, because they are direct memory access semantics. They are uber latency sensitive, where even a nanosecond impact to latency can have an impact to noticeable impact to performance in some applications. And I've provided some of the PHY latency, like TX plus RX from pin to pipe is less than 10 nanosecond, whereas on the networking side you can spend 150 plus nanosecond even just for effect. So when we moved from 32 gig to 64 gig with PCIe Gen 6, using PAM4 signaling, it was and still is a major, because no products are out yet, but it is a major inflection point for the load store interconnect. We have to keep our latency flat, whereas we remain within a fixed silicon area constraint. Now, the other important thing in this load store IO is that they're at hundreds of lanes. So we are talking to 4 to 8 lanes. Here we are talking hundreds of lanes. So then the question is, where does the on-package interconnects fit? It's a third type of interconnect. And in my mind, it is primarily load store, because we are using today to connect homogeneous dies to offer scale-up solutions, such as in our upcoming Xeon, and even in our existing GPUs. A lot of announcements have been made to that regard. They're also used to connect on-package accelerators for higher performance. And we talked about connecting memory using, for example, memory bandwidth, HBM for large memory bandwidth. We also use it for connectivity, for connection to things like modem, radio, all of those. So what do we see with that? As you would expect appropriately, that these are thousands of lanes, right? So you can see the scale kind of goes up by order of magnitude, at least, right? And sometimes even 2 orders of magnitude as you're moving through the stack, but typically an order of magnitude, thousands of lanes on the for the on-package interconnect. Lower speed, like HBM, has got 1 to 6 gig over the 3 generations. And the main KPIs or key performance indicators for these tend to be bandwidth density, because how much of bandwidth you're going to, we need to deliver a lot of bandwidth here. Cost is, of course, important. Power is extremely important because it's sitting on the package, so it's taking away from the power budget. And power is important not just from just the picojoule per bit, but also we want to have power that is proportionate to the bandwidth usage. And by that, what I mean is, if we use, let's say, half the bandwidth, maybe my link gets utilized at 50% utilization, I want to consume half the power with very low entry and exit latencies. That's what we are looking at, extremely low entry exit latencies. Of course, the latency is extremely important here because it is on the package for a lot of the applications. And the latency here is in the order of about a nanosecond for performance critical applications. Now, that's not to say that, if you're doing a modem, you can, of course, tolerate a little bit more latency. But if I have memory, if I have got, let's say 2 sets of Xeon dies that I'm stitching together, latency is super, super, super critical, right? And as is the bandwidth density, as is the area from a cost perspective, as is the power, of course, and power efficiency. So these are the types of things to keep in mind. So in my mind, the on-package interconnect, for the most part, it resembles the load store IO, and the application-wise, it resembles the load store IO. Now let's look into this particular picture here with, what is PCI Express, what is CXL? These are the 2 types of load store IO. One, CXL basically sits on top of PCI Express. It adds a few more semantics, but PCI Express, it's 2 decades old. We have had 6 generations of doubling the data rate while being fully backwards compatible. So you can take a PCIe card that was done 2 decades back, plug it in a system that's coming out today with maybe PCIe Gen 5, it will work. 900 plus member companies. It's the ubiquitous IO across the entire compute continuum. And there are quite a few interesting learnings that we want to take advantage of in that journey, right? So everything is a journey, and the ones where you have had success, you want to make sure that you take the best of those learnings. Now, in the PCIe world, there are 2 types of memory. Even though it's load store IO, you can see that the memory that is attached to the CPU, that's the coherent memory. You can cache them. Data consistency is guaranteed by hardware. Memory, on the other hand, that is attached to the device, like the GPU. That memory is also mapped to the system memory space, but it is uncached memory. It's memory mapped IO. So you're doing direct load store for both of them, but the underlying semantics is different between the 2. So this kind of producer-consumer ordering model, it works really well in PCIe. It works well for a wide range of IO devices. For example, when you're performing bulk transfers with traditional storage, moving data in and out of a networking interface, it works really, really well. And we definitely want to preserve that usages. But for the mega trends that I talked about, we have accelerators that are emerging. They want to work on a finer grained sharing of data with the processor. So for that case, we have augmented the PCIe mechanism. Like I said, CXL is built on top of PCIe. So it is PCIe plus it, and it basically does some coherency semantics and some memory semantics. With that, what happens is now devices can cache the system memory or coherent memory anywhere, and memory attached to the devices can be mapped to the system coherency space. So what happens is that now all of a sudden you are able to take the memory, cache the memory in the system, as well as be able to map the memory that are attached to the devices into the system space. So devices, different types of devices and CPUs in the system, they act as peers effectively. So with CXL, we enable that heterogeneous computing and disaggregation. Memory resources anywhere in the system can be shared efficiently between these computing elements due to the memory and coherence semantics. This results in enhanced movement of operands and data. Furthermore, because we are using CXL with memory semantics, we can basically deploy CXL for memory bandwidth and memory capacity expansion while supporting memory tiering across different types of memory. CXL as a standard is also an open industry standard, 160 plus members. We formed CXL in 2019. We're right now working on the third generation of the specification, again, fully backwards compatible. All CPU, GPU, memory storage vendors are in the consortium. Tremendous movement in the industry, and several interop announcements with real products have come out. CXL is poised to be a game changer in the industry. So what makes these two standards successful, at least in my mind? One of them, actually a few things. One is, as I said, multi-generational backwards compatible evolution. So what that does is it makes sure that your investments are protected. As a developer, you can make your transition to the newer technology at the cadence that is appropriate for your particular segment. For example, if you're doing storage devices, the cadence with which you are going to move is different than if you're doing a networking devices or if you're doing a GPU. So, not everybody will move one fine morning. You can't turn off the switch, turn on the switch, and everybody will be there, right? So this way of evolution across different generation in a backward compatible manner helps the transition, helps people innovate. Next is a huge ecosystem. It's the wide availability of IP, wide availability of tools. There is a compliance program with full plug and play. That's very important component, right? You need to make sure that if I design something, how do I make sure that it interoperates, especially if you have these kind of member company numbers that you have. So it's my strong belief that on package interconnects, we should leverage that PCI Express and CXL infrastructure for standardization, as well as for the load store usages. We need to seamlessly move the functionality from the node level to the package level to the die level, as we can see in the next slide here. What we need to really think about is the same software, the same IP, the same subsystem being applied from the node level as shown over here to the package level as shown over here to the IP level. So this basically will offer us the economies of scale, the time to market advantage, and most importantly, a seamless user experience. So for example, we can see a world where you have a multi-socket server system at the node level as shown here. Now, some of that functionality may be integrated into the package. You can see that this picture looks similar on a package level kind of scale. You can still have external memory. You can still do, the CPU to CPU, package to CPU package coherency link. You can still do PCI Express link. You can still do CXL link, but you can build this kind of a package for the specific uses that you have at the package level. And an example is our own Stratix 10. You got the FPGA, you got some DRAM connected to it for delivering memory bandwidth, and you got some what we call the IO tiles, right? Some of them can connect to like a PCIe or a CXL slot. Some of them can connect to the networking. So you have that in a given package. So that makes sense for those kind of usage. And in some cases, we might decide to integrate into an SoC. So examples include like NIC integration, on-die accelerator, even in some of our SoC offerings. So different things we need to be deployed at different places, from SoC to package level to the node level, depending on the type of application that we have. So now let's talk about the on-package interconnects, some of the opportunities, some of the challenges that it poses. Okay. So Gordon Moore, who famously predicted the Moore's law, also said that, hey, there will be a need for on-package integration. We are already living in that world, as you can see from within our own product lines that span client, server, HPC segment, and it's it's part of, in my mind, an extension of the same Moore's law. So the question is, what are some of the drivers for the on-package chiplets? Now, with Moore's law and Dennard scaling, as well as we pack more and more performance in a die, we are up against the reticle limit. We could pack even more, right? Now, with advanced process nodes, smaller dies do offer better yield optimization. So we really need to stitch multiple homogeneous dies to deliver scale-up performance. And as I said, different segments might need different number of dies to deliver the performance, which also works great for on-package integration. Next is the increasing design costs, especially at the leading process edge node. And you can see here, it's a little hard to read through the graphic here, but you can see, the costs are increasing tremendously in the graph on the right as the process nodes start to shrink. Now, so that means that, at least initially, only the necessary and advanced functions that really need the advanced process node need to be done in a die in that particular one. For example, we can have cores that is in an advanced node, and let's say part of the on-core in one of the older process node, the one, for example, with IO functionality. We basically have to do this kind of die disaggregation across different nodes, and it's already in the mainstream CPU products. You can see a lot of the products, SoC products that have done on-package integrations. Sometimes chiplets offer time to market advantage, and also they do offer a late binding option. For example, if you are doing a PCI Gen 5 to a PCI Gen 6 transition, you can just change that part or that die that does the Gen 5 to the Gen 6, and you have a market, you have a different product out altogether without really having to redo all of that SoC. So it offers that. You can mitigate risks basically in that way. Now, we also see the need for doing custom silicon for different customers, leveraging the same base product. So for example, different people may need different accelerator function, or different usages for the same customer might need different acceleration functions. So, in that case, doing the on-package integration, especially for the type of a plug and play kind of thing that I'm going to talk about, becomes extremely important. We also see different process nodes that are optimized for different functions. The examples are like, memory, logic, analog, co-packaged optics. Makes sense that they are all in different process nodes. One of the other most important reason is performance, and specifically memory bandwidth expansion. By adding more and more DDR channel to feed all the cores is getting challenging due to the high pin count and how high pin count that each DDR channel puts on the package, right? 200 signal pins. So, we can see that with CXL, we're trying to solve that problem. But with HBM, for example, we can get a very high bandwidth, power efficient, and low latency access to memory, and that can deliver us the performance that we need. So it's a combination of all of these things that are the driver for on-package integration. So what are the key metrics and what are some of the challenges? So one of them is the bandwidth density is a key metric. So this is both the bandwidth per shoreline as well as the bandwidth over area. It's important for die disaggregation. We want to have similar performance, whether we have one large die or we have multiple smaller dies that are stitched together. And it's a function of the data rate that we are deploying as well as the bump pitch that we have. Next, also equally important is energy efficiency in terms of picojoule per bit. And I talked about how that's important from a peak bandwidth usage, from a partial bandwidth usage, and from an idle power point of view, and also getting in and out of the low power states, entry exit times being extremely small. This is again very critical to deliver power efficient performance at the package level. We talked also about latency, end-to-end, TX plus RX. It's a critical component. These are load store accesses. So, latency has a huge impact on the performance that we deliver. The other metric is the channel reach. Typically it has implications on the cost. So it depends on the application, depends on the technology. And it also has an impact on the type of frequency with which you can run and the bit error rate that you're going to get. For example, if you're doing advanced packaging, the dies have to be placed in close proximity, whereas if you're doing organic traces on a 2D kind of a package model, it allows for cheaper. It's much more cheaper, but and it allows the dies to be placed apart. You do get lower bandwidth and density, but these are trade-offs, and these are real trade-offs. For some usages, something makes sense. For other usages, something else makes sense. And the key for us is to make sure that we are enabling all of those usage models through the on-package interconnect, right? Especially if you're going to deploy it as a standard. Reliability and availability. So reliability typically we measure as FIT, which is the failure in time, number of failures in a billion hours. We want that to be very close to zero, much less than 1, right? So because this is on the package, as even we do for the fit on the external interconnect, of course, the on-package interconnect also need to follow the similar model, especially very important for server HPC kind of applications. We also want the availability to be very high. So think of several nines. Cost is another component. And as I said, organic versus advanced packaging. So the question is, what are the challenges? Actually, we have a lot of technology challenges. We can pick and choose between different usages and segments because we got all of these technology challenges, which is a good thing. But choices, sorry, a lot of technology choices, which is a good thing. But at the same time, it makes it challenging to do a common silicon. Also, how do we evolve a backward compatible solution through these major technology transitions? That's something that we need to think about upfront. Power delivery and cooling is a challenge. The other thing is repair strategy. What do we do to minimize failure, optimize package yield, and how do we deal with failures in the field? Last but not the least, interoperability. Debug. How do we get the controllability, observability, given that this is on the package? So these are all interesting challenges for us to be looking into. So, the technology choices, we talked about it. You can have 2D, you can have 2.5D, for example, like our EMIB, or you can have 3D stacking like our Foveros. And from an IO or in just a physical IO point of view, there are two broad things that we see. One of them is the parallel, which is many wires, much simple IO. The other one is few wires. And these are typically your serial complex IO, like SerDes kind of IO that people deploy. Things like the various OIF standards. I've seen some people even deploy PCI Express. Each of them has their advantage and disadvantage. That primarily the many wires in the parallel side, they offer the low latency, the low power, simple design, and scalable performance, most importantly, both from a performance point of view, but also from a power efficiency point of view. So parallel in my mind naturally fits to the stringent key metrics that are needed across these usages, especially for the load store kind of usages. And we just need to make sure that our transitions across the technology migrations over the years is seamless, because that's what will dictate how successful any standardization effort can be. So let's talk about what are some of the things that are needed for doing a standardization thing. So there are 4 major things in terms of standardizing any kind of a interconnect, and also applicable for the chiplet ecosystem. We'll go from the bottom here to the top, but you can see this is the picture. These are the two dies, and this is the interconnect. And the question is, can this be like what I call a plug and play kind of an interconnect on the package, right? So the first one is, of course, the die-to-die I/O. This is the physical layer, the electrical stuff, any kind of training, link training, all of those things, bump arrangement, characteristics, electrical thermal characteristics, what type of substrate you have, what kind of interposer you have, the length budget, the picojoule per bit, the bit error rate, the reset, clocking, initialization, test, repair, all of those things, right? They get covered here. And this one gets a lot of attention, which is good. And again, a very necessary ingredient, but by itself, it's not successful. It's not enough to drive a successful and widespread standard. So the moral equivalent would be we would define a PCI PHY and then say, hey, whatever protocol you run is, bring your own protocols. They won't interoperate, right? So that's stating the obvious. Next, we have to make sure that we do the die-to-die protocol from data link layer to the transaction layer. And again, this is needed to make sure that the chips do interoperate with one another. We could map things like PCIe protocols, just like on CXL, we mapped the PCIe protocol as CXL.io, but we added a couple more. You could map CXL protocol. We can give a raw interface for somebody if they just want to do their own proprietary thing, right? So these are not only that, we also need to define some of these internal cut lines as from the IO side to the protocol side in order to develop plug and play IPs. And a parallel would be like a pipe standard, for example, that PCI Express pipe is used with PCI Express. It's used for CXL, right? So it defines how the electrical part, the analog part talks to the logic layer stuff, link layer and above. So we define those using, so we need to drive those as standards. So that way different IP vendors, you can plug and play different IPs coming from different IP vendors. That's the purpose of that. Then comes the SoC construction issue. Well, if you're using PCI and CXL, some of that is a gimme because they have solved that issue. But effectively, are dealing with how do you come out of SoC reset, initialization, all the register access mechanism, how do you define security? All of those are extremely important, right? And as I said, pretty much, both PCI and CXL have solved these, right? And they have been going at it for many years now. Next comes the chiplet form factor, right? What's the die size? What's the bump location? Power delivery, thermal characteristics. If you have to take some external pins out, where do they need to be placed? All of those things needs to be thought through, right? And specified as appropriate, right? You may not be able to specify, for example, any external pins that are going to go out because somebody might use 10, somebody might need 100, right? So, but at least from the die-to-die perspective, we need to specify those very precisely so that people can, your implementation is guaranteed to interoperate, right, across the board. Now, here are the ingredients, right? To ensure a thriving and successful interoperable chiplet ecosystem. This is leveraging the decades of experience that we have in driving widely successful industry standards like USB, PCIe, CXL, all of those, right? Of course, you need a broad market that is driving the innovations. You need the capabilities of manufacturing, packaging, testing, right? So these are the demand has to be there, and the fundamental technology capabilities have to be there for anything to be successful. We need to have products which are chiplets. Most importantly, we need to have a chiplet-based broad attach points, SoC attach point for these chiplets to thrive. In an IO world, we had platforms where volume CPUs, for example, for decades have not just one, but many open PCI slots where the broad ecosystem can innovate on. So using a similar analogy, we need to have volume SoCs embracing whatever is that standard to offer open standard chiplet interconnects so that the ecosystem can innovate on package. Right? So otherwise, what am I going to, I might have some really cool ideas that I can, I've solved some very interesting machine learning problem. I can put it in a piece of silicon. I want to put it on the package. But if different SoCs have different interfaces, then I have to spin my silicon every single time and go through the entire. Effectively, it's like designing another piece of silicon from scratch, right? So that becomes very hard to do. So you need all of those. So you need of course, the ecosystem to innovate, and also you need the volume SoCs, right? There are some SoCs that have the volume, right? And they're different for the different segments of the market. Handheld has a different set than client, then server, and so on and so forth. So you need the volume SoCs to embrace the open ecosystem. We need to have, of course, the IPs, the verification IP or VIP, and we need to have a common sets of tools and methodologies that this broad ecosystem can leverage, and focus on innovation rather than worry about how to do interoperability, right? So in other words, once you want to almost give them like a menu of choices in terms of different IPs, different VIPs, that of course they can choose to do their own in terms of that interconnect interface. But we want them to focus really on the other side, right, where they're solving the real problem using these interfaces. So that's where having all of these, plethora of tools, right, that are again proven out in the market, that helps with that adoption. And of course, you need to have an open die-to-die, standard die-to-die interface that will have compelling KPIs, key performance indicators. First of all, you need the KPIs. You need, like I said, the volume attach points. You need to have a specification that is very thorough. And you need to have something that satisfies the need of a wide segment of the market. If you start doing things for the niche, then that becomes a barrier of entry, right? In the sense that people always make decisions based on the the volume with which they're going to ship, right? Because everything is an investment, they need to get the return on the investment. Now let's look into what are some of the characteristics of this die-to-die interface. Of course, you are going to do the die-to-die specifications. These need to be very well defined specs, right? No room for ambiguity. Somebody can read the specs, go and implement it. And it is going to work with somebody else reading that spec and implementing it, right? The two should be able to come together and work, right? That's the goal. So you need to define the electrical, like we talked about, the logical, the protocol layer, the software. How does software talk across this link, right? How do the discovery works, right? All of those things you need to solve. How do you do error reporting? Things of that nature, right? Form factor management. So again, in a lot of these, right? The standards have the load store interconnects that have been standard for many generations that solved a bunch of those problems. So as appropriate, you could use those, but there might be other applications where you need to do this completely from scratch, but we need to define all of these. We need to define C&I, stands for compliance and interoperability test specification. These are test criteria based on those specifications. So if you define something that, hey, this needs to be the electrical characteristics, you need to define how are we going to test it? What does passing look like? What does failing look like? That criteria needs to be very crisply called out in a specification that talks about how to do the C&I for the die-to-die. We need to have test hardware and test software, so that if I designed a part, I can bring it there and I can make sure that it's going to interoperate. So this will have the test criteria will be compliance, it will be the interoperability, those will be the criteria. Once you apply it, there are two clear outcomes. Either you passed or you failed. Hopefully you passed. But even if you didn't pass, that's fine. You know exactly where it failed. Maybe there are 2 or 3 things that you need to go back to the design, fix it, come back and test it. And in general, people would, without going to an interoperability workshop, they would apply the same thing in-house and figure out, whether they're passing or failing. So effectively, what you're looking for is a predictable path to design compliance with open standards. And that's the essential ingredients to make sure that a lot of the developments that happen are going to interoperate across the board, right? And you want to make sure that as a die developer, if you have developed something, it's going to work across a broad range of SoCs that you may connect with. So, and that's basically these set of steps, right? If you follow, that's going to effectively increase your chances. There are no guarantees, but it's going to significantly improve your chances that once you put it in a real platform, it's going a real package, it's going to and run many weeks worth of tests. You're going to keep on running. Right? So
Debendra, 10 minutes, okay?
Yeah, well, I'm done, almost done.
Okay.
So some of the feature directions and conclusion are, I hope, I have made the case where chiplets and die-to-die interface are essential to the compute continuum. We need to deliver power efficient performance. We need it for yield optimization, different functions, custom solutions, cost effectiveness, right? Die-to-die standardization is essential to develop an open ecosystem. The open plug and play slot, we need to come up with a terminology, equivalent terminology on the package side, but effectively a slot at the, think of a slot at the package level will unleash a lot of innovations, right? And that's good for the broader ecosystem. It actually helps everybody, lifts all the boats, and there is a tremendous value to be accrued by all the participants. And evolution needs to track the underlying packaging technology. As I said, that's going to be a challenge for us to make sure that how do we evolve, right? In a backward compatible manner. Where does it make sense to break backward compatibility? All of those need to be really well thought out, right? For delivering this compelling metric. And these are again, if the problems were easy, if we would have done it, somebody would have done it long back, but we need to together go and solve this, right? There are these challenges, things like debug. How do you do the observation? How do you do backward compatibility across this technology transition? All of these things needs to be overcome. And as I said earlier, we need to keep in mind, what constitutes a very successful open ecosystem, right? The four ingredients that we talked about. We need to keep each and every one of those in mind and deliver something that is going to lay the foundation for an open chiplet ecosystem, not just for 1 year or 2 years, but hopefully for decades. Right? Successful standards last at least for a decade through at least 3 generations. Thank you. I'll take any questions. I don't know if you have any.
Yeah, please, if you have any questions, please enter them in the chat, and I will read any questions from the chat. Debendra, thank you very much. I think it was very interesting to see the big picture perspective on how the die and package level interconnect fits into the bigger picture. I'd also like to mention that with regards to standards for chiplets, that we have a presentation tomorrow morning talking about the work of the chiplet design exchange working group that are working on those very issues. Are there, I don't see any questions yet in the chat. Are there any questions from the live attendees in North Carolina?
I do see one question in the chat now. Does everyone have any questions in the room?
Oh, okay, yes, there's a question from Frank Leach. Please comment on the die-to-die BOW emerging open standard, focusing on the technical pros and cons.
So as a matter of principle, I do not comment on any existing standards. So, of course, we know the bunch of wire standards, yeah, given that I'm involved in multiple standards, I generally do not comment on any standards about their pros and their cons.
Okay, not even on.
And in general, yeah, BW stands for bunch of wires. It's being developed by ODSA under OCP, and you can make your own conclusion by looking through the KPIs that I talked about. I just don't get into that unless I can talk about PCI Express as a standard, because That's where I'm personally involved in. I can talk about it. I can talk about CXL because that's where I'm personally involved in. I can talk about it. Things that I respect as part of the different consortium work on different things. So if you're given that personally I'm deeply involved in other consortia, I do not talk about consortia in which I'm personally not involved in, and I'm not authorized to speak. So.
There's a question from Bob Connor. Do you have any comments on power delivery, interconnects, and standardization?
Sure. I think again, right? I mean, as we talked about, if you want to put multiple dies on the same package, especially if you're talking about 3D stacking, right? We need to solve that, and we need to make sure that those get solved in not just power delivery, also cooling, all of those things, right? We solve that in a consistent manner across different implementations.
Okay, there's another question from Durand Jarrett Amor.
Sure.
For USR links, although using links that operate at lower speed helps to keep the design of the transceiver simple, wouldn't having transceivers that operate at higher speed, say 10 gigabit per second or more?
But it is the bump count, and yeah.
Oh, you can read. Okay, well,
I
I'll
can
read it anyway.
Yeah.
Reduce the bump.
Sorry, go ahead.
Okay, go ahead.
Let
me finish reading the question. Wouldn't it help reduce the bump count and thus allow for more power bumps, for example, which could help with power integrity issues for these massively parallel links?
Sure. If you're, for example, trying to do, let's say, some kind of optical kind of conversion, then that makes sense. And again, for certain kind of applications, those interconnects make sense. They do, but if where the high frequency but bumps, right? I mean, at the end of the day, it is the bump. Also, it is the area behind, that area of the circuit behind that bump. It's no longer actually bump limited. It is limited by something else that is sitting behind it. That basically dictates the bandwidth density. So my comment is that, simpler design with many wires, parallel wires, they offer better bandwidth density and they offer better power efficiency. And that's basically, if you're thinking about, and by the way, much better latency. Okay, so these are well-known things that that's what they help you with. And so if you're doing, for example, load store IO, the many wires kind of thing makes sense. Running at a lower frequency, what you want to do is run. You're not really targeting for the highest speed. You are targeting for a lot of them being packed together that are consuming very little power that you can turn on and off quickly. Right? That's basically the goal that you have. And you're still at the end getting much more bandwidth density, much higher bandwidth for the same area. You're getting much lower power for the same bandwidth, and you're getting a much better latency picture.
Okay, are there, one follow-up from Durand. That make, you want to read the question and then answer it?
Yeah, that makes sense. But what about signal routing issues with thousands of signal routes? Just curious. So yeah, thousands of signals gets routed. Typically, you would do that using micro bump, and in our case, you would do it like using an EMIP, which is passive silicon, also can be active silicon. So that's not an issue. Think of it as those routing happen, or if you're doing like a stacking on the like a Foveros kind of a thing, it's just a bunch of micro bumps that you place on top of each other. So that's not an issue. They're not really getting routed across a long distance, right? If you're routing across a long distance, then then you're basically at that point you have to do the bumps, and your bandwidth density will go down. So.
Okay, well, thank you very much, Debendra. That was very, very enlightening. Our